Hi folks, in this video our goal is to determine a formula for the derivative of a quotient of two functions. Okay, and in particular what I'd like that formula to contain is the derivatives of the individual functions. Okay, but as we saw with the product rule, we may find other expressions in that formula. Okay, so we've already determined that this is not equal to the derivative of x over the derivative of g. So we are going to see if we can find a formula that's reasonably easy to memorize. Now, one way to try to do this is to do what we did with products, which is to use the limit definition and see if we can manipulate that expression to find a nice formula. Okay, and it certainly is possible to do it that way. However, if we can somehow determine a formula by using something we've already established, that's even better. And since division is closely linked to multiplication, we're going to see if we can get through it from there. Okay, so the first thing I'm going to do is I'm actually going to define this function, give it a name. So I'm going to call h of x the function which is just the quotient of f and g. Okay, now the reason why I do this is because what I'm going to try to do is take this equation and rewrite it so that it has a multiplication instead of a division. And the easiest way to do that is to just multiply both sides of the equation by g of x. Okay, so I can just rearrange this equation as h of x times g of x equals f of x. Okay, a perfectly legal algebraic operation. But what that does now is it allows me to work with this product. So the other thing I can do, since again, whatever I do to one side of the equation is legal as long as I do it to the other side of the equation, is I'm going to take the derivative of both sides of this equation. Okay. Again, something that I can do since these two functions are equivalent, their derivatives are also going to be equivalent. Okay, and this now is what allows me to use the product rule. Okay, now here the Leibniz notation, that is the ddx, is kind of useful because especially of the left-hand side, as I have this product, I didn't want to use big brackets with an apostrophe there. That's a little messy. So in this case here, using the Leibniz notation was useful. Okay, however, in the next step, you see that I'm going to switch to the prime notation, which is perfectly fine. In fact, you should be getting used to using both notations. So let's apply the product rule to this left-hand side. So the product rule says that the derivative of the product is the derivative of the first, so h prime at x, times the second function, so g at x, plus the first function, h at x, times the derivative of the second function, so g prime at x. Okay, and that's equal to the derivative of f at x, which I'm going to write as f prime at x. Okay, now let's see how this equation can be useful. Let's remember what it is that we're trying to determine. We're trying to determine the derivative of f of x over g of x. But remember that we defined f at x over g of x as being equal to this new function h. Okay, and of course this can be written as h prime at x. Okay, so essentially what we have to do is we want to isolate this expression in my equation. Okay, so let's do that. So I want to isolate h prime at x. Okay, so first I'm going to bring this addition to the other side. So I have f prime at x minus h of x g prime at x. Okay, and then I can divide g of x to both sides. All right. So just to be clear as to what we're finding, let's remember that this here represents the derivative of f at x over g of x. Okay, so again, just to show that we're finding exactly what we're looking for. And here, what I don't want to see on this side of the equation is that h of x. I'd like everything to be in terms of f and g. So I can rewrite this as f prime at x minus h is just f at x over g of x times g prime at x all over g of x. And so what I've managed to do is to find a formula for the derivative of a quotient in terms of the individual derivatives and the individual functions. So that's the good news. The bad news is that this is a complex expression and not really one that's easy to memorize. Okay, so I think what we're going to try to do here is we're going to try to simplify this a little more to get something that's a bit more user-friendly. Okay, especially I don't like this idea of having a fraction inside a fraction. Okay, so let's go ahead and try to simplify this a little more. So the first thing I'm going to do, as we often do in these scenarios, is I'm going to subtract the numerator so I could get one single fraction in the numerator. Okay, so here I'm going to use a common denominator. Well, the only denominator I have is g of x, so I'm going to put everything in the numerator over g of x. Okay, so this first expression does not have a g of x in the denominator, so I'm going to multiply that to the numerator. So f of x times g of x, okay, minus this expression already has the g of x in the denominator, so there's nothing I need to do to this numerator. Okay, and this is all going to be over g of x. So this represents the numerator here, and of course all of this is being divided by that g of x. Okay, but this can be simplified even more. So here I'll show all the steps, even though I think a lot of you are going to see what's going to happen here. So if I take this numerator, which is this whole expression, okay, and I'm dividing this by g of x, but remember, when we divide fractions, that's the same as multiplying by the reciprocal. So this is like multiplying by the reciprocal of this function, which is just 1 over g of x, and we see that these two just multiply. So what I'm left with in the end is f prime of x, g of x, minus f at x, g prime at x, all over g of x squared. Okay, and this is something which is much more compact, a lot nicer than the one we had here, and again fairly easy to memorize because we notice that that numerator looks pretty similar to our product rule. Okay, we still have f prime g and f g prime, except we're subtracting them and we're dividing by g of x squared. Okay, and this is what we call the quotient rule for derivatives. Okay, so not as nice as just the derivative of the quotient is the quotient of the derivatives, but something that is, relatively easy to memorize. So if we look at an example here, so let's say I want to use this to determine the derivative of, x squared over x cubed minus x. Okay, now notice that this here is not easy to do via other methods because I can't split this up into two terms here, okay, because of this subtraction in the denominator. So in this case here, I kind of have to use something like the quotient rule. So let's follow this. So what does the equation say, or the formula say? First, I have to take the derivative of f, but think of f as representing the numerator of this function, and g is the denominator. So I'm taking the derivative of the numerator, which is 2x, okay, and I'm multiplying it by the denominator function. So x cubed minus x, okay, minus the numerator function, which is just x squared, times the derivative of the denominator function, which is just 3x squared minus derivative of x is 1, and all of this over the denominator squared, so x cubed minus x all squared. Okay, now certainly you could simplify this out, okay, especially that numerator will simplify quite nicely. Okay, however, for now, we're just going to practice applying the formula. Okay, so again, this is just how we were able to determine a formula for the derivative of a quotient, and we did so by recycling our product rule. Okay, and this is an example here of how we apply this formula to the derivative of a quotient of two functions. Okay, that's it for this one.